In a previous movie, we discussed how the membrane potential of pacemaker cells changes over time. The x-axis for this graph down at the bottom here is time. The pacemaker potential brings the membrane potential from resting to threshold. Calcium channels open, which creates the depolarizing phase of this action potential. Potassium channels open, which causes the repolarizing phase of the action potential. And then again, the pacemaker potential begins the process. Now, the rate of heartbeats is the rate at which action potentials are initiated. And what changes is not the duration of action potentials, but the length of time between action potentials. And so it's this pacemaker potential, the duration of the pacemaker potential, the slope of the pacemaker potential that determines pulse rate. The longer the duration, the slower the pulse rate. The faster the duration, faster because it has a higher slope, the quicker the heartbeat is. Okay, so there are two neurotransmitters delivered by the nervous system which change heart rate by sending neurotransmitter to pacemaker cells which dictate heartbeat rate. The first we'll look at is the adrenaline-like noradrenaline molecule. So it's a neurotransmitter, drops this off right at the cell surface. And when norepinephrine or noradrenaline interacts with the receptor for that substance, it interacts with what is called a stimulatory G protein. So the stimulatory G protein is launched from this connection with the receptor over to adenylate cyclase. So now it interacts with adenylate cyclase. And when it does so, it increases the rate of the enzymatic process converting ATP into cyclic AMP. Cyclic AMP then acts as a signal molecule which changes the shape of the funny channels in such a way that when they're open, there is increased flow through those channels. So notice they're only going to be open when threshold potential, when membrane potential is below threshold potential. So anywhere down here, anywhere below 45, those channels will be open. When they're open, if there's lots of cyclic AMP, there'll be more flow through those channels. And if there's more flow through those channels, you're going to, let me change the color here, you're going to now have a slope that's increased, which means these action potentials will come more frequently. Oh, do I dare draw an action potential? I'll try. So now you have a situation that looks like this. That action potential is going to be just the same length as it was, but this pacemaker potential is going to be quicker. So you're going to go like that. Now you see you've gotten many more action potentials per unit time, therefore your pulse is increased. So the key is that more sodium enters when the funny channels are open, which shortens the period of time it takes between heartbeats by increasing the slope of this pacemaker potential, because the depolarization happens faster. Now let's look at what happens if you add signal from the parasympathetic nervous system. So before we showed that norepinephrine, which is the neurotransmitter sent by the sympathetic nervous system, will increase the pulse rate. Acetylcholine is the neurotransmitter that the parasympathetic nerves will deliver. When it's delivered, the receptor for acetylcholine will release the inhibitory G protein subunit. When that inhibitory G protein subunit is attached to the adenylate cyclase, it's going to decrease the rate of enzyme activity, meaning that less cyclic, I shouldn't have drawn it there, less cyclic AMP is being generated. When there's less cyclic AMP being generated, when this channel is open, less sodium is going to enter. And if less sodium is going to enter, that would reduce the slope and increase the duration of the pacemaker potential. But this interaction also leads to the opening of another channel. This is a ligand-gated channel, sometimes called an acetylcholine-gated channel, that allows potassium to move through the membrane. Potassium is driven by the concentration gradient from the pump, and so you're moving potassium ions out at the same time as these sodium ions are coming in. Remember, there's fewer sodium ions coming in, so that reduced the slope. Now there's a bit of potassium ions going out. That's also a relatively polarizing thing. Remember, it's potassium leaving. Here, that's actually repolarizing the membrane. Here, many fewer potassiums are being let out, but some are being let out. And so the combination of the two leads to quite a decrease in the rate at which the potential moves from, it's not a very big decrease. Maybe that would be the decrease with just the channel opening, and maybe this is the combination of the channel opening and less flow through the funny channels, and then the same duration of action potential. And now you're going to have a slower, so you see that you've extended the time that it takes to action potentials to occur, and over time that difference in how long it takes is going to be very evident as the heart rate slows. So to review, acetylcholine causes a change in shape of the receptor for acetylcholine. The inhibitory G protein slows down adenylate cyclase activity so that less cyclic AMP is being made per unit time. Less cyclic AMP, cyclic AMP is the molecule that speeds up the flow through this channel, and so if there's less of it being made, then you have a reduced rate of sodium entry combined with a slightly increased allowance for potassium to leave the membrane, and that really slows down the pacemaker potential, longer duration pacemaker potential, slower heartbeat. Okay, so duration of pacemaker potential sets the pulse. The longer the duration, the slower the pulse. The molecules that are involved include two neurotransmitters, one from the sympathetic system called noradrenaline or norepinephrine, one from the parasympathetic nervous system called acetylcholine. One of these speeds up the rate of adenylate cyclase. One of these slows down the rate of adenylate cyclase. Adenylate cyclase leads to the manufacture of cyclic AMP. The amount of cyclic AMP in this area dictates how fast sodium enters through funny channels, but only when funny channels are open. Remember, funny channels are only open below threshold potential. Another thing you could think about is how adenylate cyclase rate influences the rate of heartbeat. So if this is my graph, and this is adenylate cyclase activity, it's possible that the regulation of the inhibitory and stimulatory proteins, G proteins, are having a competitive inhibition and activation effect, in which case you would have a situation which look like this. So this would be stimulatory G, and this would be inhibitory G effects on AC. What's the x-axis? What's the y-axis? Yowza.